This is some work that goes back a few years. The main result is together with Mabel Iglesias Ham. And it's based on some earlier work which had nothing to do with packing at first, with Michael Kerber, who was postdoc at ISD with me. Apparently the two liked this work and they got married and they moved to Graz, and now they have expecting the second child. But the whole talk is sort of, it weaves in and out of what we did then. And it's about soft packing. So maybe I say a little bit about the motivation. And it's particularly soft packing in R3, mostly because we live in 3 dimensions. And soft packing comes up, for example, in biology, where cells are more or less roundish, but they're not really spheres. And when they pack, they become more polyhedral, I guess. Like you squash them together like oranges. If you squash oranges, we can pack them tighter. Something like this, but I don't want to deform the shapes or the spheres that I pack, but rather I let them overlap a little bit. And then the work really got started, I think this was 2016 or 17, when pictures of the packing of DNA in cells started to appear. And they are, I don't know how much you know about it, but they are wound up in more or less spherical shapes. But they are connected because the DNA is connected. And then how the DNA is stored says a lot about how it functions inside of the body. But this whole thing is not tightly packed because things have to be accessible and they're squishy. And so Caroline Uhler motivated this problem at that time, and they considered soft sphere packing by allowing a certain threshold of overlap. And I always had a disliking for the threshold parameter because it's an extra parameter. So I was thinking of something that is parameterless, and that's what I want to talk about today. But let me get started maybe about packing and covering in general. And there are 2 particular point configurations or lattices in 3 dimensions which play a big role. And the first one is called the body-centered cubic lattice. And if you don't know about this, it's the integer lattice, plus you also add the centers of the cubes that the integers form. So to make my life easier, I double it up. So I use only the even integers. And then inside of the cubes formed by the even integers, I put the center. That's the body center. So this is the BCC lattice. And the fundamental domain of that has size 4. So I denote it by the norm of the lattice. And the way you see that is that the cubes of side length 2, they have volume 8, 2 to the 3rd. And I have twice as many points. So I give each point only half of the 8. So that's 4. And that's also going to be the volume of the Voronoi cell of a point, which in the case of the BCC lattice looks like that. This is called the truncated octahedron, or you can think of it as a cube intersected with an octahedron. And importantly, every vertex has degree 3 here, and they pack space because every point gets such a truncated octahedron. And around each vertex there are exactly 4 cells. This is what's called a primitive cell decomposition. And when you look at the packing efficiency, which I get by, at every point I grow a sphere until the spheres start to touch. And when they start to touch, I stop. In this case, it's for radius square root of 3/2, not important. But the density is 0.68 in this case. That's the part of space covered by the spheres. and the remainder is not covered. But I can also use this lattice for covering. And in covering, I blow up the spheres further. I let them overlap until they cover the entire three-dimensional space. And then I stop growing. This happens at square root of 5/2. And the density in this case is 1.468, where the 463. This is the waste, like how much the spheres overlap and not necessary because it's covering twice or three times. And I would like to compare this with the FCC lattice. This is well known as the densest sphere packing, face-centered cubic lattice. So here, what we do is we take the integer grid. Again, I take the even integers. And for every cube, I add the face centers. So horizontal, so the horizontal faces, the side faces, and the front faces. Get three of them. In this case, the volume of a Voronoi cell is 2, because I get 4 times as many points as the lattice, the integer lattice, and it looks like that. So that's a rhombic dodecahedron. And I always thought that the truncated octahedron is a nicer polytope than a rhombic dodecahedron, because the rhombic dodecahedron is not even simple. Look here, there are degree 4 vertices. And there are 6 cells around such a vertex when you pack. And this corresponds to the octahedron in the dual of the Voronoi cell packing. Okay, so when I look at the density for packing, it's higher. So it's 0.74. And Tom Hales proved that this is indeed the highest that we can do in 3 dimensions. But for covering, notice that the FCC lattice is much worse than the BCC lattice. It has more waste than it actually covers. So that's why I usually prefer the BCC lattice, and I route for the BCC lattice. But unfortunately, for our result in soft packing, the FCC lattice beats the BCC lattice just by a little bit, as we will see later. Okay. Now, a more theoretical exercise is to think of the space of lattices, just to get a basic orientation. If you identify lattices when they're related by a rotation or scaling, then you get a 5-dimensional space of lattices. There's various ways of arriving at these 5 dimensions. But it's kind of tricky to see how this 5-dimensional space is connected. Now, what I would like to think of is, for each lattice, I look at the Voronoi cell, and then I would like to take all these lattices that have combinatorially equivalent Voronoi cells. So for example, I would have a cell for the truncated octahedron. And because this is a simple polyhedron, this will be 5-dimensional cell. And the other cells, so there's 5 known, or known to be 5 combinatorially different Voronoi cells, namely the truncated octahedron, we saw it. The rhombic dodecahedron, we saw it. There's also a version of that, the hexarhombic dodecahedron. And then there's a hexagonal prism, which you get when you do a layer, hexagonal layer, and on top of another hexagonal layer. And then you get these prisms, hexagonal prisms. And the cuboids, which you get for the integer grid. And those are the only 5 different cell types, Voronoi cell types. And therefore, I get a decomposition of this 5-dimensional space in only 5 cells. And only one of them is actually 5-dimensional, namely the cell that corresponds to the truncated octahedron. And the others are lower dimensional. So this is maybe interesting to keep in mind, that this twisted cell of the truncated octahedron really determines this whole 5-dimensional space. And what I would like to do today is I would like to look at a one-dimensional family of lattices. And this one-dimensional family will go straight through this five-dimensional cell of the truncated octahedron. And then it will hit the cuboid cell. And then it will go along the rhombic dodecahedron cell. So if I didn't make a mistake, the rhombic dodecahedron cell is only three-dimensional. So it's really a coincidence that it can actually get along or inside of this three-dimensional cell in five-dimensional space. When we constructed this one parameter family, we had no idea, but that's how it turned out. All right. So perhaps I start with a diagonal family of lattices. So that's a one-dimensional family or a line of lattices. It will contain the BCC lattice for epsilon equal to 0.5. Epsilon is going to be my parameter along the line. Starts at 0, only positive epsilons. Otherwise, I get the cubic lattice at 1.0 and the FCC lattice at 2.0. And here is how it's constructed. It's easiest to explain when I start with a integer lattice. So there I have a cube. I have three vectors at a right angle each. And if I look at the plane that goes through the endpoints of these vectors, I get a hexagonal grid. And my points are in several of those, in infinitely many of those parallel planes. Between those planes, there are no points. And in this family of distortions, what I do is I either squish the planes closer together or I stretch them apart. What this means is, if I look at the unit vectors u1, u2, u3, so here's a right angle, I add epsilon minus 1 over 3 times the diagonal vector, which is the sum of the three unit vectors. So for epsilon equal to 1, I get 0, so I get just the integer grid, and otherwise I get this deformation. I prepared a little movie that I've drawn for you. So here, but only in 2 dimensions. I was not able to do it in 3 dimensions. Here's the Voronoi, or a piece of the Voronoi tessellation of the integer grid. And now I move the planes of lines of points together, the lines of points together. And you see how the squares become hexagonal. Here I reached the perfect hexagonal grid. And let me go back to the square grid. And when I pull it apart, I also get hexagons. But notice that from squishing together, the extra line is here. I assume you see my cursor. When I pull it apart, the extra line is here. So in a dual Delaunay triangulation, the edge flips from this direction to that direction, the diagonal edge. So then it stretches out, and then I go back. Okay, I also did this for packing. Integer grid, move them together. You see how the packing gets denser. This is a hexagonal grid, pull them apart. Oh, my computer is a little slow, doesn't keep up with my drawing. And here I get the hexagonal grid also, but I just missed it. It's now further apart. And now I go back. So what happened in the plane that both when I push it together and when I pull it apart, there are strategic places that are occupied by the BCC and the FCC lattice. They are both hexagonal lattices. But you could also do this in higher dimensions, and you also get interesting lattices this way. They're all different, only in the plane they're the same. Oh, by the way, what is the policy for asking questions? So this thing with a chat room is a little indirect. We could also try that you just interrupt me in a talk. And unless this gets out of hand and we have to mute everybody, we could work this way.
Can I interrupt?
Sure.
Sure. This reminds me of the flip and flow. It's the same thing. You start off with a packing, a triangulated packing, and you break one, and then you get you get another one. It's very similar to this. That's just a comment. That's all.
Okay. Okay. Well, let's see. How do we continue here? So for this, this is three-dimensional again. This drawing shows the upper curve is the covering density of the lattices that you get in this family. So the family runs from left to right. So epsilon from 0 to 3 roughly on this chart. And for each configuration, you get the covering density. So you see the minimum at 0.5. That's the BCC lattice. The cube lattice is very bad. It's this local maximum, actually a cusp. And the FCC lattice is again a minimum, but it's not as good as the BCC lattice. And these curves are analytically computed, so they are precise. I can write down the formula. At the bottom, this dashed line is the packing density. And you see again, the BCC is pretty good. It's a local maximum. The FCC is better, also a local maximum. And the cube lattice is again a local minimum. So the cube lattice is very bad in terms of covering and packing. And the solid line in between, that's the soft packing. But I need to explain what it means, because the soft density is a little different defined, so they're not entirely comparable, but you see somehow how it follows the packing, more or less. Okay, so this is telling you the result. But here's the theorem about soft packing. That among all the lattices in this one parameter family, the FCC lattice maximizes the soft density. And I'm going to define what the soft density a little bit later. I denote it by delta 1. Delta itself is the classical density, and delta 1 will be the soft density. And maybe as an aside, this soft density is obtained when the spheres are 1.09 bigger than the spheres for packing. So the extra 0.9 tells you how much they overlap. And I think this 1.09, that's exactly 12/11. And I'd like to say a little bit about why we can prove these things. Mostly it's because the Delaunay triangulation, or I call it the Delaunay mosaic of the lattices, is almost always the same combinatorially. Namely, for the entire family, I have the same Delaunay mosaic for epsilon between 0 and 1 combinatorially. And then again, the same for epsilon larger than 1. So I really only have to deal with 2 cases. And not only have to deal with only 2 cases, each case itself is symmetric, so that all the simplices or the cells that appear, they are symmetric. So I only have to always talk about 1, 2, or 3 or something of the cases. So this controls the explosion of cases. So here is, in the 3-dimensional case, the compressed integer grid. So this here is when I had two planes of points and I've pushed it a little bit together. So instead of cubes, I get this hexagonal truncated octahedra as Voronoi cells. And I also draw the centers of those octahedra. And then I connect them by edges if they share, if the Voronoi cells share a face. So of course they form this cubic structure, but they also share these little hexagons and these little rectangles. So when I add those also, I get this triangulation. So this is it's known as the Freudenthal triangulation. And maybe I say a little bit about the Freudenthal triangulation. So the Freudenthal triangulation of a cube is obtained by calling one vertex, the one at the cursor 0, 0, 0, and the other one 1, 1, 1. And when you travel from 0, 0, 0 to 1, 1, 1, you can do it by replacing one of the zeros by a 1. So you do this 3 times. And this is a walk on the edge skeleton. And when you do such a walk, so this is one walk, for example, then you take the convex hull of the walk. This is one tetrahedron. If you make a different choice, you can first step the same, then you go this way and that way, you get another tetrahedron. So there are 6 different ways of going up there. So you get 6 tetrahedra, they all go around the diagonal. And they all have the same shape. And this structure is true for epsilon positive, but smaller than 1. When epsilon is larger than 1, you get a different Delaunay mosaic. Namely, you don't get a triangulation, but you get what I call a decomposition into slices. So the interesting slice here is between the 2 tetrahedra. There's a tetrahedron in front, there's one in the back, and in between you get an octahedron. And maybe it's easy to see why this arises, because you start with a cube in a distortion. And for the cube, all the 8 vertices lie on a sphere. But then when you stretch it in a diagonal direction, the middle 6 vertices, they still lie on a sphere. But the first and the last vertex, they get off the sphere. And so the middle one, they stay on a sphere and they form this octahedron. And also this decomposition, this mosaic stays until large epsilons. So these are the 2 cases that we have to consider. Actually 3 cases, because at exactly epsilon equal to 1, we have the cube decomposition. So there the Delaunay mosaic is just a cubical decomposition. All right. So this is our simple setting. And now about density and soft density. Let me first talk about the classical density. So I call my lattice lambda. I have a radius r, which means that around every point of the lattice, I draw a sphere of radius r. They could be overlapping or not. At the moment, I don't care. And then the density is the volume of the ball. I'm a little conflicted of calling this a sphere or a ball. In sphere packing, it's called a sphere. In topology, a sphere is something different. So I write BR, but I call it a sphere. So anyway, so it's the volume divided by the volume of the Voronoi cell. That's the density. But I would like to make it more complicated. Because I would like to think of this density as some kind of expectation in a random experiment. For example, I could define pi sub k as the probability that a random point is contained in exactly k spheres. And this is defined because the decomposition of space is periodic. So I might as well just choose x from the Voronoi cell. And then, so I pick a random point within the Voronoi cell. And then now that is exactly in k points, that I call this pi sub k. And this probability is also the volume of the subset of the Voronoi cell covered by exactly k spheres. Okay, so phi sub k is the probability that I am contained in at least k spheres. So it's pi sub k plus 1, etc. And with this terminology, then delta becomes the expected number of spheres that contain a random point. So this is phi sub 1 plus phi sub 2 plus phi sub 3. Or write it like this with probabilities pi 1 twice pi 2, 3 times pi 3. Okay, but I really like this intuition of the expected number of spheres that contain a point. So this is the density, and I explained the FCC and the packing and the covering in this classical notion of density. Oops. My picture got smaller once of a sudden. Be careful how I touch the computer. Soft density. All I'm doing is I penalize for double covering and triple covering, etc. So it's going to be the probability that I'm in at least one sphere minus the probability I'm in at least two minus at least three, etc. Okay, so this is my notion of density. And it's not entirely a random choice because we struggled a lot with finding the right formula. And I'll talk a little bit about this. But before getting into that, when you do this soft density in 2 dimensions, then it turns out it's the same thing as maximizing the probability that I'm exactly in one disk. And this is a problem that was studied before. So the packing of disks that you maximize the probability of being in exactly one disk is again the hexagonal lattice, and there's a little bit of overlap. So it looks roughly like this, although this is not a perfect drawing. This was proved for lattices by Ballas in 1973 and proved to be the optimum also among non-lattices by Blind and Blind in 1986. And if you wonder what this configuration exactly is, so there's only 2 fold overlaps, and the length of the segments of overlap and non-overlap and overlap and non-overlap, they're all the same. So since I overlap with 6 other disks, I have 12 segments. And so each segment on the boundary of the circle is 1 hour. That's the optimal configuration. So that's probably the wisdom behind the design of our clocks. I will need some volume formulas, so I'll introduce a little bit of that. So how I translate the probabilities into volumes. For this, I introduced 2 notions, the kth Voronoi cell and the kth Briand zone. The kth Voronoi cell was introduced by Gabor Fayez-Todt in the 70s. Namely, the usual Voronoi cell is the first Voronoi cell, and the kth Voronoi cell collects all the points x such that the 0, which is a point in a lattice, is among the k nearest, which means there can be at most k minus 1 lattice points closer to x than 0. So you can imagine the kth Voronoi cell is bigger than the first Voronoi cell. It's not convex anymore. I think I have a picture. Let's see. Yeah, in a plane. So the yellow stuff is what the Voronoi cell is a square of the middle point. If I add the yellow triangles, I get the second Voronoi cell. It happens to be convex. It's a coincidence. If I add the cells which are neighboring to those yellow cells, I get the third one, and so on and so forth. So how do I get this picture? Well, I draw all the bisectors of 0 in the middle with every other point in the lattice. So here I chose the square lattice because it's easier to draw. I draw all the bisectors of the subset of points I have here. And then I collect cells in this arrangement. And I'm in the kth Voronoi cell if I get to the point by crossing at most k-1 lines, where I walk on the outside. I cross a line only once. And the Brillouin zone is the difference between two consecutive Voronoi cells. So the yellow is the second Brillouin zone. And the next color is blue, I believe, is 1, 2, 3, 4, 5, 6. That's the sixth Brillouin zone, I believe. And here is a simple property of Brillouin zones. Namely, they have the same volume as the first Voronoi cell. And the reason is also clear, I think, because here the blue is the sixth Brillouin zone of 0. I can draw the sixth Brillouin zone of every point in a lattice. They're all disjoint from the interior, and they nicely tile the plane. So they must have the same, they must share the area, just the same way the Voronoi cells share the area, or in 3 dimensions, the volume. So somehow as the K-Brillouin zones, they become more and more spherical, but they're kind of thick, or not entirely thin, and the volume stays the same. So this is my first claim here, that the volume of the kth Brillouin zone around any point in a lattice is just the norm of the lattice for every k and every p. Okay, it's useful for us is the second. If I'm interested in the probability that I'm in at least k spheres, I can take the intersection of the kth Brillouin zone with a sphere of radius r and normalize. And this gives me the probability. So I imagine a sphere centered at the origin. It covers some part of the sixth Brillouin zone, and the volume of that part gives me the probability. And for example, the next claim then follows that the first soft density, or the soft density, delta 1, is by definition twice phi 1 minus the sum of the phi's. I was just rewriting it. The sum of the phi's is the classical notion of density, which is the volume of B of the sphere divided normalized. And twice phi 1 is twice the volume of the intersection of the sphere with first Brillouin zone. So this is a kind of a nice volume formula for the soft density that I'm going to use. Okay. I use this last volume formula to prove unimodality of the soft density. And this is important for our analysis. And that's why I said somehow the soft density is not arbitrarily chosen. It's chosen so that it's unimodal. So let me first talk a little bit about general unimodality and then about why the soft density is unimodal. So I call a function unimodal. I need it differentiable. If it first grows, then it has a maximum and then it shrinks. So it has a unique maximum. And then this unique maximum, I call this an equilibrium position. For example, if you have a star-shaped region and a point in the kernel of that star-shaped region, this is akin to a kth Voronoi cell of this point in the middle. And then I grow a sphere, and I keep track of the volume of the sphere inside of this star-shaped region. Wait, I think I made a mistake. I'm not looking at the volume. I need to draw to connect it to this graph. What I consider is, I consider the length. Here it's a disk. The length of the circle inside of the yellow body minus the length of the circle outside the body. And at the beginning, everything is inside. So my function starts at 1. The fraction inside is 1 until my circle starts to get out of this body. Then it starts to shrink. And then it reaches 0 when there's equally much inside and outside. And then it becomes negative. And I claim there's a single intersection for this if it's star-shaped and the center of the circle is in the kernel of the star-shaped body, because the fraction can only go down. And if I have such a situation, then if I integrate this function is unimodal. Because at first it grows. When I reach rho, that equilibrium, it had the maximum, and then after that it shrinks.
So you're computing the length of these curves, right?
I compute the length of these curves, but then I integrate, so I get the area.
Oh.
Where I cheated a little bit because I talked about fractions, so I don't get exactly the area, but I have to multiply with the length, which keeps changing. So it's slightly more complicated, but not much. And that proves the unimodality. Before we proved this, I always thought that unimodal functions are probably in some kind of parameterization, they're convex or concave functions. So there's a single maximum. In this case, I don't think there's any parameterization that makes them concave. At least I didn't see any. But somehow through this kind of argument, I can prove unimodality. And I think unimodality, here I just want to say soft density is unimodal. With this argument together with some volume formulas that I introduced. But I would like to mention like why unimodality is useful. The reason it's useful is because when you have a lattice and the soft density is unimodal, then this means that there's a unique radius. So you could grow as the spheres until it reaches this maximum, this equilibrium position. That's when it's maximum, and growing further, it shrinks again. So for each lattice, I have a unique radius, which gives me the maximum soft density. And then after that, I only have to worry about changing the lattice. But for each lattice, I get a unique answer and I compare them. Without unimodality, I don't have this unique answer, and this is trouble. Too much trouble for me anyway. And to give you a feeling of that not everything is unimodal, here is a natural measure which is not unimodal. So this pi1, remember pi1 is the probability that my point is in exactly one sphere. This is not unimodal in 3 dimensions. It's unimodal in 2 dimensions. That's why the Balázs proof worked out well, but not in 3 dimensions. And here is my example. If I have spheres along a line equally spaced, and then maybe higher up there's again spheres, but right now I'm just interested in those, and the other spheres are further away. I can make this part of a lattice. Then the Voronoi cell of the middle center is this slab of parallel planes. And when my radius reaches the distance between 2 adjacent points, I have this configuration. And maybe you remember Archimedes' theorem for spheres, that if you cut a sphere with two parallel planes, the area between, and here I mean a topological sphere, the surface, the area of the sphere between the two planes is independent of where the two planes cut the sphere, as long as both planes cut the sphere. So this means that the area of the middle sphere, so they look like disks in a drawing, but they are really spheres. So the area of the middle sphere is the same as the area of the left and right intruder sphere. Okay, so the areas are the same. And then now, if I grow a little bit, the derivative of the volume is the area. So if I grow a little bit, there's no change. And the configuration of the yellow configuration also stays the same. It's always an arc from left line to right line and two arcs from right line to left line for the intruders. And so it becomes a toroidal thing with same area on the middle sphere as for the other two. So this means that as I grow, pi1 stays constant. So first I go up, then I reach a plateau, and then this plateau will eventually break when the other spheres intrude. But anyway, there's not a unique maximum, there's infinitely many maxima here. And I couldn't, in 3 dimensions, I couldn't make this bimodal or something where I really have more than one local maximum, because I do have a plateau here. But in 4 dimensions, I can make this as many maxima as you like. So pi1 is not a good measure, not a good soft measure for this reason, or at least one that's more difficult. Okay, and for the rest of the time, which 15 minutes or so, I can give you the optimality proof that why FCC lattice is optimal. And I try to, I start with an exercise to prove or to calculate the soft density for the FCC lattice. And as you know, the FCC lattice, they have a sphere that touches 12 other spheres. And so I'm going to grow the spheres a little bit so they overlap. And I let them overlap so that pairwise overlaps. These caps, one cap is exactly 1/24 of the whole surface area. And I need 1/24 because I have 12 of them. So 12 of these caps need to have exactly half the area, because that's the equilibrium position. Half the area in, half the area out. I get this 1/24 when the radius of the sphere is 12/11 of the packing radius, by Archimedes' theorem again, because I know exactly how big the area of the cap is. Okay, so now I can compute the soft density. Phi1 is, let's see, this is half the sphere. The first factor 1/2 is just because the norm of the lattice is 2. So forget about this one. I take half the sphere and I take I take 12 cones. Right, so this is the part of the Voronoi cell that's covered by the sphere. Phi2 is I take the cones negative, because I'm interested in this segment outside the cones. And the cones all together with these segments, make exactly half the sphere. And so I just have to subtract the cones and then I get these segments. And then Phi1 minus Phi2. So in this case, I don't have triple overlap for the FCC lattice. It's therefore 12 times the cones, and then this normalized gives 0.844. Just to get a feeling of how this works. If this makes sense, let's see what's next slide. Ooh, this is big. Okay, make it smaller. This is the truncated octahedron. And after a slight compressive motion in my diagonal lattice, in my diagonal family of lattices. And what I would like you to think of is there's a lattice point in the center of this truncated octahedron. And when it grows, it meets the faces and the edges and the vertices of this truncated octahedron at different times. But this whole thing is symmetric. So it reaches the front face at what I call F1, these rectangular faces F2, the little hexagons in F3, the long edges in E1, the short edges in E2, and the vertices at V1. Everything is symmetric. For example, all the vertices are actually on the sphere. This is inscribed in the sphere. I call this critical radii, because when a sphere grows and when it passes a critical radius, then there's a new overlap. When I pass a face, I get a double overlap, and an edge, I get a triple overlap. And so I have to compensate for all of this. But there's only 6 things that I have to keep track of. In the elongated version, epsilon larger than 1, I also have 6 F1, F4 for this face. I call it F1 because this is actually the same critical radius as for the truncated octahedron. Then two edges, 2 types of edges, and the vertices, again, there's only 1 type of vertex. So these are the only critical radii that I have to keep track of. And I'm not going to explain these formulas, and I just show them that they exist, which means that for every epsilon, I know exactly when the critical radius is reached when I, for example, pass the big face of the truncated octahedron. So I have these formulas, and this over the entire range. That gives me complete control of what's happening. But still, a tricky thing is when I compute the equilibrium situation. Because the equilibrium situation, I need a formula for the volume and for the double overlap, which is doable, but we didn't manage the triple overlap. So we made our life easier, and we forgot about the triple overlap, which you get with this, what we call the simplified soft formula, delta 1s. So I get this when I only look at the spheres and then a double overlap of spheres. And there's some complications that we have to deal with in the end. But in any case, if there's no triple intersection, the simplified and the soft density are the same, right? Because it's phi1 minus phi2. But here, this is minus 3 times phi3, whereas in a soft density, it's minus phi3. And because I subtract more here, the simplified density is, in general, less than the soft density. Something to keep in mind. Oh, now I can increase my page size again. Okay, so the rest is case analysis. It's not quite as bad as usually in sphere packing, but then we also solve a smaller problem, only 1 parameter family. And the case analysis says that, so rho is my equilibrium radius, that in this range of epsilon, so this is very compressed, the only critical event that I get before reaching the equilibrium is I cross the face that's marked F3 in my cube octahedron. In next range, I cross 2 faces. Here I cross 1 face. Here I cross 2 faces. Here I have, so for example, the second case is 2 and 3 together. This is because once I have F1 smaller than F3, And then I have 3 smaller and then have 1. And I didn't differentiate between these 2 cases, but I label them with different Roman numbers. So we see that all the way until case 9, there's no edge crossing. There's no edge event, which means there's no triple intersections, which means that the simplified density is the same as the soft density. So I can do all the computations perfectly, and I have to worry about the triple intersections only be for epsilon beyond 2.34. Okay, but for the simplified density, soft density, I can compute the soft density analytically, get this nice curve. It is also the soft density up to around here, where my cursor is. And so we can compute stuff for the FCC, it's 0.84, forgot what the rest was. And then BCC, it's ever so slightly smaller. And here it seems to decay fast anyway. So the triple intersection cannot do much, but to get a proof took us a while. So then we had to go into the details. I didn't make any slides, but roughly what's happening is in this range where I pull things apart, I go already beyond the FCC lattice. And if you remember what's happening after the FCC lattice, the sphere in its plane has 6 neighbors because it's a hexagonal grid. And the spheres grow so that the 6 neighbors touch in a packing case, the sphere. And if I pull it further apart, it doesn't help anymore. It just pulls the planes apart, but the spheres cannot grow further. So I just get this configuration and I pull it apart. It's a little bit like the universe, which seems to be pulling apart everything without any other effects. So there we made up another density function that we could control, and that majorizes the soft density, and we were able to prove that this density function remains below this high value at FCC, and therefore we concluded that indeed the FCC lattice is has the highest soft density among the 1 parameter family that I outlined. And with this, I thank you for your attention.
Thank you, Herbert. What a really nice talk. Are there any questions? So if people can't speak up, they're welcome to write in the chat and I'll read out questions.
Is there, in the packing case, there's 2 different packings that give the same density, but for the soft packing, that's not the case.
Well, for the packing case, the second, which is as efficient as the FCC, is not a lattice. It's a double lattice, or I don't know what you call it. And I don't know whether, yeah, I think the same phenomenon you see in soft packing, because you could just, it's sometimes called hexagonal close packing, HCP.
Mm-hmm.
And if you take a HCP configuration and use the sphere sizes, I get the same soft density.
Very nice talk. What would you say the prospects are for extending this sort of analysis beyond this 1 parameter family to other lattices?
I didn't say anything about it.
Yeah, I'm asking what you would say.
Yeah. What would I say? Yeah. I don't know. I'm kind of hopeful, but we tried a little bit, but not as serious as we should maybe. I think I would like to understand the 5-dimensional space better to make reasonable choices about how to explore the rest of the space. because it's not clear to me that the 5 dimensions are actually necessary. Maybe there's some extra dimensions can be neglected by proving that in this direction it only goes down or something. And my understanding of that 5-dimensional space is a little limited. That's currently what I perceive as the obstacle.